Hello everyone, welcome to week 9 of the problem solving session for the course Material Energy Balances. So far we have been looking at different types of energy balance problems, and today we will discuss a slightly different topic, humidity charts, psychrometric charts, which are very useful in solving both material energy balances. So, brief introduction about myself. I am Chandra. I'm your NPTEL PMRF for this course. I'm doing my PhD in the Department of Chemical Engineering at IIT Kanpur, and I work in the area of tissue engineering and bioprinting. If you have any queries related to the course content, feel free to drop your queries in the course discussion forum, and you can also reach out to me as well in my email. So every Saturday for the past 8 weeks, this is week 9, we have been meeting like this from 3 to 5 p.m. All the sessions are recorded, so they are made available in my YouTube channel so that you can view it afterwards as well. And the notes used in this discussion sessions, in these problem solving sessions, they are also made available to you. If you just log in into your NPTEL account, you'll be able to see it. And every session, an attendance is also noted. So let's begin. Okay. So these are some terms that you would see in a psychrometric chart or humidity chart. So how does psychrometric chart looks like? This is a psychrometric chart. And we will try to locate the parameters used in this chart, which are very useful for determining the properties of air, how much moisture is there, and like enthalpy and everything. Like it's very easy. It makes the energy balance and material balance problem solving much more easier if you have this chart with you. So in this chart, you would see a quantity called dry bulb temperature, which is basically the temperature of air at dry conditions, which you can measure using a thermometer or thermocouple. So it is in the x-axis, x-axis of this chart. All right, this is dry bulb temperature. So this chart comes in both SI units as well as in degree Fahrenheit as well. So don't get confused. So for today's session, I am referencing only to the psychrometric chart presented in SI units. All right. But the other one, it looks exactly the same. Only thing is instead of degree Celsius, you will find degree Fahrenheit. Instead of kilojoule, you will see BTU as a unit. Instead of kg, you will see pounds as the unit for mass. Okay. So this is your dry bulb temperature, this S-axis, starting from -10 to 5 degrees, 55 degrees Celsius. Then absolute humidity. All right. So absolute humidity is basically the y-axis, also termed as the moisture content. It tells you what is the actual amount of water in vapor state is present per kg of dry air. All right. So these are these two x and y axis. Then relative humidity, also represented as HR. So you see these kind of curves going, these curves with percentage written over it. So these are HR or relative humidity curves. Okay. So we have in this chart up to 100%. This is 90, and the last line is 100% relative humidity. Okay. So these three are important. Now, if suppose someone asks you to find dew point or DP, but first let's understand what is DP. DP is the temperature at which humid air becomes saturated if it is cooled at constant pressure. So the chart I am showing you is at constant pressure 1 atm. Okay, the pressure in used or the pressure considered for making this chart is 1 atm, and they have used a reference state of liquid water at 0 degrees Celsius and the dry air at the reference state of 0 degrees Celsius and 1 atm. These are the reference states. So at 1 atm or at constant pressure, the temperature at which the humid air becomes saturated means the relative humidity is 100%. Okay, that temperature is called the dew point. So we have to basically, in order to find dew point, what you need to know the dry bulb temperature first. Okay, so if suppose you are given the dry bulb temperature of 10 degrees Celsius and you are asked to find the dew point, so it will be, how will you find it? You have to draw a vertical line from here till the 100% relative humidity curve, which is the last line, this line. Okay, and you would see that for this example it is coming to be 10 only. Okay, so wet bulb temperature, sorry, dew point is also 10, but let's go to a higher temperature. I took a very bad example, but it's fine. So let's go, what is the dew point? Okay, if or how much temperature decrease you want in order to make the air completely humid if the initial air has a temperature of 40 degrees Celsius. Okay, that's the question. So if the temperature is 40 degrees Celsius, the initial air temperature is 40 degrees Celsius, and with respect to this, you want to find that dew point. How would you go? You have to first draw a horizontal line. So you also need another parameter. You not only need to know the temperature, a dry bulb temperature, but you also need to know initially how much relative humidity is there. So let's suppose initially in our example it is 10%. Okay. So we have to first draw a line till 10%. So initial state of the air is it has a temperature, dry bulb temperature of 40 degrees Celsius with the relative humidity of 10%. So how much, uh, at what temperature, then at what temperature it will become completely humid. Okay, so for that you have to draw a horizontal line like this towards the left direction. Make sure you draw a straight line. Okay, and where this horizontal line meets this saturation, 100% saturation curve, you have to extend a vertical line downwards. And what you'll see, temperature is 2 degrees Celsius. So the dew point at the condition 40 degrees initial condition for 40 degrees Celsius and 10% relative humidity is 2 degrees Celsius. All right, it will become much more clearer as we continue with some problems based on this concept. But for now, if anyone asks you, all right, what will be the dew point for temperature this and relative humidity this, you can use the psychometric chart to calculate the dew point. Okay. Then what is the humid volume? Humid volume is another quantity that is also represented in the psychometric chart. By definition, it is the volume occupied by 1 kg of dry air plus water vapor. Okay, that is the humid volume. So humid volumes are basically, let me clear this. So humid volume are basically these steep diagonal lines. All right. So there are only four, 2, 3, 4, 5. So there are only 5 constant humid volume values given: 0.75, 0.8, 0.85, 0.9, and 0.95. All right. So in order to get the value in anything in between, we have to do some interpolation. So again, let's go back to the same example. Let's say someone asks you, what is the humid volume for temperature 40 degrees Celsius at the given condition of 40 degrees Celsius and 10% relative humidity. So we have to first extend a vertical line to 10% relative humidity towards 10% relative humidity starting from the 40 degrees Celsius. Then at this point, at this particular point, we have to, using a scale, if you are doing it offline, like not using an iPad like me, using a scale, we have to attempt to draw a parallel line parallel to this line. This is the uh, line given for 0.9. So from we have to draw a parallel line that passes through this. Okay. So what you see, you should get a value closer to 0.9. So we have to do a linear interpolation here. So what I do, so it is 0.85 and 0.9. So what I do, I just first determine what is the difference between the 2 points. It is 0.05. And how many markings are there in between these 2 points? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, they are close to 18 markings. Yeah, let's consider it 17 because we want to take the markings only in between 0.85 and 0.9. That means each marking corresponds to close to 0.003. Okay. And where this point have come from, relative to 0.9, this point is around 1, 2, 3. 3 markings away. That means it should be approximately 0.89. Okay, so you can like do a similar thing to find an approximate humid volume at the given condition. Okay, now if you have understood dew point, humid volume, now let's understand wet bulb temperature. Okay, so how to calculate wet bulb temperature? So if you see, wet bulb temperature is given here, right? So in order to calculate wet bulb temperature at, so what is wet bulb temperature? It is a temperature that you get when you take a thermometer and wrap around a cotton wick around its bulb, which is wet. Okay. So as the surrounding, if it's warm, let's say, there is some evaporation because of which the thermometer bulb cools down, and then you see a drop in temperature. So that is the wet bulb temperature. So if suppose someone asks you to calculate the wet bulb temperature at 40 degrees Celsius and 10% relative humidity, then what you have to do, you have to draw a diagonal line. Okay. And from here, extend a vertical line. Okay. So this temperature that is coming to be close to 18.2 is your wet bulb temperature. All right. Don't confuse it with dew point and the wet bulb temperature calculation. In dew point, we had to extend a horizontal line towards left. Okay. Whereas for calculating wet bulb temperature, we are drawing a diagonal line following these diagonals. Okay. So that's how you can calculate wet bulb temperature from a psychrometric chart. Next, specific enthalpy of saturated air and enthalpy deviation. Both are related, that's why I'll show you both together. So if you see these lines that are outside, they represent enthalpy at saturation, means when the air is 100% humid, right? That is at that state, what is the enthalpy? And if you see this kind of curves, what they are called enthalpy deviation curve. Okay, so they're called enthalpy deviation curve. Now, if someone asks you what is the enthalpy at saturation, let's say at 40 degrees Celsius and 10%, then if you see this line that we extended like this in diagonal fashion, okay, if you follow this line and follow it much further towards the scale, you can easily say that enthalpy saturation is close to 53 kilojoule per kg, but it is enthalpy saturation. Now, what is the enthalpy at a given condition? That is 40 degrees Celsius and 10%. So for this, you have to subtract this value 53, no, for first you have to see what is the percentage deviation. So what is the, well, not percentage, what is the deviation first? So this point lies between curves, this curve and this curve. This curve corresponds to minus 0.8 deviation, and this line corresponds to minus 0.6 deviation. So it lies in between. All right. So if I quickly do again the similar linear interpolation thing, it is minus 0.6, 1, 2, 3, 4, 5, 0.255, 0.04. So how far is it? It is into 3. Minus 0.72. This point corresponds to an enthalpy deviation of minus 0.72. And you saw the enthalpy saturation is 53. So at the given condition, your enthalpy or specific enthalpy will be 53 minus 0.72. That is 52.28 kilojoule per kg of dry air. All right. So that is how you can calculate specific enthalpy at the given condition, right? By using the enthalpy saturation and enthalpy deviation curves. So you see, they have given enthalpy deviation curve starting from minus 0.05 to minus 1.2. Okay. Now, if everything seems clear now, we will continue with some problems based on this theory. Let's clear this chart. We would need this chart to solve the problems. This is the first problem that we have here. We have to use the psychrometric chart to estimate first absolute enthalpy, absolute humidity, that is, in short, it is written as HA. We have to write absolute humidity, then wet bulb temperature, TB, humid volume, it is represented as V hat, dew point, and specific enthalpy. At 35 degrees Celsius and 20% relative humidity. Okay. These are the this is the condition and at which we have to find these values. So let's start with the easy one. Absolute humidity. 35 degrees Celsius and 20%. So this is 35. 20%. This is the moisture content or absolute humidity. We have to extend a horizontal line from here to directly in the right direction. And what you see? 0.007 kg per kg dry air. So it is kg water per kg dry air. Then wet bulb temperature. From this point, we have to extend a diagonal line like this. And from here, extend a vertical line. And what you get? 18.9. This is your wet bulb temperature. Then humid volume. At this point lies in between 0.85 and 0.9. And as I already mentioned while I was explaining, that each marking here corresponds to close to 0.003. So here there are 17 markings, if you remember. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So there are 17 markings in between. So each marking corresponds to 0.003. And then what is this value? One, two, three, 4, 5, 6, 7, 9. So it will be 0.85 0.85 plus 7 into 0.003. Okay. And you should get 0.871 approx. So this is an approx value. Okay. So that's your 0.871 meter cube per kg dry air. And what is the dew point? From this point, you have to extend a horizontal line and draw up a vertical line like this. You should get 8, close to 8 degrees Celsius, or 8.1. 8.1 degrees Celsius. Then what is the specific enthalpy? From this point, your enthalpy at saturation is close to 53.5. And what is the enthalpy deviation? So it lies between minus 0.4 and minus 0.6. Okay. And there are how many points in between? Around 7 points. So here, from from the curve minus 0.4, it lies around 5 points away, and each marking is around 0.03. So you should get minus 0.55. Okay. So we have to subtract this value like this, and you would get 52.95 kilojoule per kg dry air. All right. So this is how you will complete part 1. All right. Now part 2 asks you the amount of water in 150 meter cube of air at these conditions. So 150 meter cube of air is there, and per kg of dry air, which I'm shortening as dA, contains meter cube of volume of air, water, sorry. Okay, volume of water, and In 1 kg of dry air at this condition, the mass of water is 0.07 kg. So this value, this second term, is essentially taken from V hat or humid volume, whereas the third term is basically your absolute humidity. When you perform this calculation, you should get 1.19 kg water. Okay. So in 150 meter cube of air, there is 1.19 kg of water. All right. This is easy. Now, similarly, we have to try this, try this problem. And this problem also has a bonus question. We have to compare the amount of water obtained in part A, in question 1 and question 2. So here the condition is 50 degrees Celsius and 20% relative humidity. So I guess that at 50 degrees Celsius and same relative humidity, the amount of water will be uh, less 50 degrees Celsius in comparison to 35 degrees Celsius. Let's try to see numerically and see whether I'm correct or wrong. So at 50 degrees Celsius and 20% relative humidity, first, what is absolute humidity? Let me remove all this. Fifty degrees Celsius, this is 50 degrees Celsius and 20%. So this is your vertical line. The amount of uh, moisture at absolute humidity at this condition is this point is approximately close to 0.01575. Okay, so 0.01575 kg water per kg dry air. Then wet bulb, humid volume, dew point, and specific enthalpy. So let's calculate the wet bulb now. So here from here We have to draw a diagonal line like this. And from this point, we have to extend a vertical line. The wet bulb temperature that you got is around 28.3. degrees Celsius. Then humid volume. So this point lies in between the curve -1 and -1, 2. So here there are 3 points. So each point is close to -0.06. And this point particularly lies at the second point. So you should get close to -1.12. Okay, this point is close to -1.12. Oh, I'm sorry, I did a mistake, a very silly mistake. These curves are your enthalpy deviation curve. For determining humid volume, you have to consider this 0.95 and 0.90. Okay. So with respect to this curve, 0.90 is quite far, but let's see how many points are there. Close to 16 points. Okay, close 16 points, and there's a difference of 0.05. So each point is again corresponding to 0.003. And this point is closer to 0.95. How close? Around 4 points away. This means you should get close to 0.938. That is your humid volume. Meter cube per kg dry air. What is the dew point? So you have to draw a horizontal line and then extend it. So it is coming close to 20.3, I would say. Then what is the specific enthalpy at this condition? From this point, we have extended this diagonal line. If we extend this further, we are getting around 92.5. That is the enthalpy saturation, minus what is the enthalpy deviation. Now you have to consider minus 1 and minus 2. Okay, each point is corresponding to minus 0.06. So minus 1 plus minus 0.06 into 2. It is minus 1.12. You get 91.38 is the specific enthalpy. So then what is the amount of water for the same volume? (150 meter cube). Then we divide it by humid volume that we got. And 1 kg multiply it with absolute humidity. Per kg air. And you should get 2.152, close to 2.52 kg water. Now this is for the condition of 50 degrees Celsius, 20% relative humidity. The amount of water in the air is only 2.5 kg, whereas for 35 degrees Celsius, the amount of water that you are getting is 1.19 kg. So, at 35 degrees Celsius, the amount of water that it is holding is much less. So, yeah. Now, let's move to the next question. Now, this question uses a psychrometric chart for doing material and energy balance. Right. So read the question. Air is at 27 degrees Celsius and 80% relative humidity. And it is cooled to 11 degrees Celsius at constant pressure of 1 atm. So use the humidity charge to calculate the fraction of water that condenses, right? We have to calculate the fraction of water that condenses and the rate at which the heat must be removed. Q dot to deliver 1000 meter cube of humid air at the final conditions. So this is a question where you are basically cooling the air from a higher temperature to a lower temperature. So like the AC. So let's try to draw a flow chart for this process. So let's say this is your air cooler and 1 kg of dry air is entering. Why? Because we are considering a basis of 1 kg of dry air. The same basis that they use to make the humidity chart as well. Okay. And it is at 27 degrees Celsius. Let M1 be the mass of water vapors that is there in the air, and the relative humidity HR is 80% currently. Now, two streams are going out from the air cooler. One corresponds to the air, okay, and this air is at 11 degrees Celsius now. Let M2 be the mass of water at 11 degrees Celsius in the vapor phase. And another stream that we are getting is of condensate, whose mass, let's say, is M3. That condensate remains liquid water. All right. And this is also coming out at 11 degree Celsius. Now, the enthalpy, let's say, for the inlet air is specific enthalpy, let's say, is H1 hat kilojoule per kg unit. For the cold air, let's say it is H2 hat. And for the condensate, it is H3 hat. Okay. Now from the chart, the psychrometric chart, let's find first for the condition 27 degrees Celsius and 80% relative humidity. Let's find absolute humidity and enthalpy. 27 degrees Celsius and 80%. This is 27. 80% means this curve. So we have to draw a line towards this curve. This is 80%. The absolute humidity at this point is close to 'okay, sorry. So I took the wrong vertical line. Should be here. This one. This is the relative humidity curve. And from here, if you see, the absolute humidity is point 0.018 kg water per kg dry air. What's the enthalpy at this condition? Close to 73. Okay, here it is 73 is the enthalpy at saturation, and this lies in between the enthalpy deviation curve of -2 and -1. So we are getting enthalpy of 72.85. So then at this condition, what will be M1? The basis is 1 kg of dry air. So M1 is the kg of water vapor. So this will be for 1 kg of dry air, 1 multiplied with absolute humidity tells you that it has 0.018 kg of water. This is your M1. Okay. So in condition 1, you now know M1, H1. Both quantities are known. Next for condition 2, at 11 degrees Celsius. Now here 1 kg of dry air is there, but it is cool, like completely saturated with humidity, which is why the relative humidity that we'll consider is 100% or saturated. So at this condition, HA is 11 degrees Celsius. So this is the line for 11 degrees Celsius. And HA corresponds to close to 0.0085. Yeah. What is H1? Sorry, H2. H2 is at this condition this is the point. Close to 32 is the enthalpy at saturation minus. Now this point here, yeah, it's 32, right? So that is your enthalpy. So what is then M2? M2 will be 0.0085 kg of water. It will be like for 1 kg of dry air, so it will be M2 will be this. So M2 and H2 both are known. Now we can do a material balance on water. We calculate the value of M3. So M1 is equals to M2 plus M3, or M3 is equals to M1 minus M2. Is M1, it is 0.018 minus M2, 0.0085. So we should get 0.0095 or 0.01. It is M3. In the question, we were asked the fraction of water that condenses. So fraction of condensate will then become 0.01 is the condensate. By how much water that is supplied, it is 0.018. Will come out to be 0.55. This is the fraction. So first part is done. Then we have to calculate the rate at which heat must be removed. So as you can understand, temperature drop is there. That means heat is removed from the system, so it will be negative. You have to calculate this value. Okay. So this is a open system. All right. Where work is zero, there is no kinetic energy, change in kinetic energy, no change in potential energy. So Q will be simply delta H, change in enthalpy. And this delta H is total enthalpy that goes in, comes out, and minus total enthalpy that goes in. So when we are talking about total, we now know H1, H2, but H3 is still unknown. All right, we have to first calculate H3. So let me do here. For calculating the enthalpy of condensate, H3, we will choose the reference state 0 degrees Celsius. Water is in liquid, which is the same reference state that they used for making this chart as well. At this reference state, with respect to this, delta H will be basically H3. And your final state is this 11 degrees Celsius. All right, and where water is in vapor state. So H3 will be is equals to Cp into delta T. Now Cp at 0 degrees Celsius and liquid water is 4.217, and the change in temperature is final minus initial. That is, you get what 46.387 kilojoule per kg water. That is the value of H3. So if we like summarize, there are two substances involved in this process. One is humid air, another is water itself. What is going in, what is coming out. So when you see the flow chart, you see humid air is coming in for at the mass of M1, and M1 is 0.018 mH. 0.018 is the mass of the water that is coming in at the enthalpy 72.85. kgs. And is water coming in? No. What is coming out? First, this saturated air is coming out at the mass of 0.0085 and enthalpy of H2, which is 32. Also, condensate is also coming out at the mass of 0.01 and enthalpy H3, which is 46.4, 46.34. I'm rounding off, right? So these are the values. So then you will be 0.0085 into 32 plus 0.01 into 46.34 minus 0.018. Yeah. So let me rectify this and this. See, humid air that came in was 1 kg. Okay. So this was M1 and M2 were the mass of water vapors in the air. But this is the total mass that came in. There will be 1, and this will be also 1 into 72.85. So what do you get? Minus 40.4 kilojoule, which is the heat removed, right? But we have to calculate what is the heat that must be removed to deliver 1000 meter cube per minute of humid air, that uh, is the requirement. So we have to convert the heat that we got into a heat flow rate. So do this at 11 degrees Celsius. What is the humid volume? 11 degrees Celsius and saturated air. Go back to the psychrometric chart. So it should lie in between 0.8 and 0.85. So I already calculated it, and the value that I got is close to, this is the value. It is close to 0.815. You can definitely cross check. Yeah. So this means what? This means for 1 kg of dry air, there is a volume of 0.815 meter cube of humid air. So then Q dot will become this heat that we just calculated into for 1000 meter cube per minute a volume of 0.815. So if you remove these values, you would get close to 50,000. The value that I got is close to 50,000 kilojoule per minute is the heat flow rate. That is the heat flow rate of removing heat from around 1000 meter cube per minute of air. Okay. So with this, I'll end today's discussion session. All right. If you have any queries related to psychrometric charts and how to use it for material energy balance, uh, let me know in the discussion forum maybe, or when I upload the video in my YouTube channel. You can also reach out to me through the comments, or you can email me as well. And I'll see you guys in the next session. Thank you for joining.